Hello, everyone. We're back again after Sasha did an overview of quantum computing. We are going in with the next topic, which is Introduction to Quantum Computing and Quantum Computing Ecosystem by Pawel Gora from QWorld. Pavel,
Hello.
hi, how are you?
Hello, I'm fine. Hello, everyone. Uh,
Uh,
yep.
yeah,
Can you
you
see
can
my
start.
slides now?
Thank you.
All right.
We can see them.
Okay, great,
Maybe
perfect.
just go full screen. Yeah.
Okay, great, fantastic. All right, so once again, hello, everyone. Welcome. Thank you for having me here. My name is Pawel Gora. I'm a board member of QWorld. So I will tell a bit about QWorld during this presentation because it's international initiative aiming to build a worldwide quantum computing ecosystem. But at the beginning, I will also tell you more about introduction to quantum computing, right? So I will just give you a bit of theory and some information about some possible future applications of quantum computing. So let's start. So maybe just a brief intro to QWorld. So QWorld is a non-profit global organization that brings quantum computing researchers and enthusiasts together. And our goal is just to popularize quantum technologies and software and create this worldwide quantum computing ecosystem in which people from all over the world can collaborate, do research, and learn together about quantum computing. So I will tell you more about QWorld in the last part of this talk. But first, as I said, I will give a brief intro to the quantum computing. So it will be just a bit or a qubit of theory. Then I will tell a few words about applications of quantum computers, and finally about building a quantum computing ecosystem. So let's start from the theory. So what is quantum computing? What are the quantum computations? So the simple answer is that these are computations according to the laws of quantum mechanics. The full answer is more complex, let's say, and I will also give you more details soon. So basically, it's of course it's not enough time to talk about quantum mechanics and even trying to understand what quantum mechanics is. But what is important from our perspective is that computation is a physical process. So we can analyze, we can design, invent, and analyze algorithms, but eventually, at the end of the day, we would like our algorithms to be implemented and then run on real physical uh, computational devices, right? And these physical devices are governed by the rules of physical world, which is inherently quantum. And there might be some interesting conclusions and also some advantages of this fact, and maybe also some disadvantages. So, for example, maybe some of you have heard about something that is called the Landauer principle, which basically says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information, like erase one bit of information. Right? So this minimum possible amount of energy, as you can see, is proportional to the temperature of the environment, and there is also a Boltzmann's constant involved. Already the conclusion is that we cannot just do computations totally for free, right? So we need some information, we need some energy, at least for some computations. So this is very important conclusion. All right, so the famous physicist Richard Feynman said in 1960s that there's nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. In fact, they may be certain advantages. As you maybe know, there is also something like Gordon Moore's law, which basically says that the number of transistors in a dense integrated circuit doubles about every 2 years. And this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. As you know, in 1960s, when Richard Feynman just stated this or formulated this sentence, computers were much larger than they are now nowadays, right? So for more than 60 years, we can observe that computer elements are becoming more and more smaller. And the question is whether this process can go on forever. So even Gordon Moore himself in 2015 said that I see Moore's law dying here in the next decade or so. And Intel, the company working in the semiconductor and processor industry, realized in the same year that the pace of advancement has slowed. So now the doubling of the density in the integrated circuit, density of transistors, has slowed from 2 years to 2.5 years. So we can already see that it's becoming more and more difficult to build more dense integrated circuits. And if this law has to be true for more years, then about 2035 or 2040, a size of a single transistor should be of a size of a single atom, more or less. And in such a scale, you can imagine that these small computer elements like transistors will not be able to operate in exactly the same way as they operate nowadays, just due to the laws of quantum mechanics and this quantum mechanical phenomena that occur in such a scale. But maybe we can just conduct our computations, maybe we'll be able to run our computations in such a scale in a bit different way, right? So the same Richard Feynman in 1983 realized that now we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function, the ones move around, the zeros move around, and finally, along a particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant. No losses, no uncertainties, no averaging. But the question is, can we do it? So can we do computations just by having a row of atoms with each atom in either of the two states? Can we do it? So since nowadays and even now we are talking about quantum computing, you can probably guess that it's possible. So we already have some initial quantum processors, initial quantum devices. So here you can see Bristlecon, which is one of the Google's quantum processors to the left, and on the right is a cartoon of this device, where X represents a qubit with nearest neighbor connectivity. Right, so we already know that we are able to build some quantum processors, and later in this talk we'll also discuss what we can potentially do with such processors. All right, but what are the differences between classical computers and quantum computers, beside the fact that we'll be operating we operate in much smaller scale in case of quantum computers? So our transistors are much smaller. There are also some differences from a perspective of just computational model, because in case of classical computers, we have bits and classical gates. So I guess that all of you know about classical gates like AND, OR, NOT, or some other classical gates. But in case of quantum computers, we have qubits and quantum gates. So what's the difference? So a single bit may be in a state that has a value 0 or 1. So mathematically, it's something very, very simple. It's element from the set 0, 1. But the qubit, in case of a qubit, the state of a qubit may be in a superposition of state 0 and 1. And you can think about the superposition as having some information about the state 0 and some information about the state 1. And mathematically, it turns out that it's something very complex, or much more complex, much more difficult than just a set with two elements, as it was in case of a bit. So in case of a qubit, it's a unitary vector of two-dimensional Hilbert space over complex numbers. So it sounds quite complicated from a mathematical point of view. Okay, but let's try to understand it. So in case of a bit, and the single state or state of a single bit is determined at each time. So we know exactly whether the state is 0 or not, and this state can be changed from 0 to 1 and vice versa. But in case of quantum computers, to get value 0 or 1, we can do a measurement which breaks superposition. And we just have probabilities of getting 0 or 1, and these probabilities depend on the qubit. and in fact of a qubit state, which is this unitary vector of two-dimensional Hilbert space over complex numbers, right? And our quantum gates may modify our qubits and states of qubits, and they can also modify the probability of getting 0 or 1 after the measurement. So this is a representation of a quantum state, which is a superposition of pure states 0 and 1. So these zeros and 1 are the so-called orthonormal base of a quantum system. So they can be also interpreted as base vectors, two-dimensional vectors in our two-dimensional Hilbert space, right? And A and B are just complex numbers, but they cannot be an arbitrary complex number. So the squares of their amplitudes are just probabilities of getting 0 or 1 in a measurement, so that the sum of these squares should be equal to 1, right? So these complex numbers A and B determine the probabilities of getting 0 or 1, and also influence the computation. So influence what might be the outcome of just processing a given quantum state using a quantum gate. We can also think about quantum states, as points on something that is called a Bloch sphere. So it can be mathematically proved that there is a correspondence between the representation of a qubit in terms of these complex numbers and sum of two-dimensional vectors and points on a Bloch sphere. So that's why sometimes we say that quantum computing, in case of a single qubit, is just a journey on a Bloch sphere, because our quantum gates may also do some operations on this sphere. So in most cases, these are just some combinations of rotations of the sphere. So yeah, these are just examples of some notable and most important quantum gates. So for example, the Hadamard's gate is responsible for just introducing the superposition, so that the pure state 0 can be transformed to a superposition of state 0 and 1, such that with equal probability, with probability 0.5, we can get 0 or 1 after the measurement. We also have Pauli gates, Pauli X, Y, and Z gates. So these names correspond to the rotations, because X Pauli gate corresponds to a rotation of the Bloch sphere around the X axis by 180 degrees, so by angle equal to pi. And it's similar for Y and Z gates. So you can see that, for example, the X Pauli gate is just our quantum representation of a negation, because the pure state 0 is transformed to pure state 1. We may also have quantum gates which operate on more than one qubit. So, for example, the CNOT gate is an example, right? So, in CNOT we have 2 qubits, or we operate on 2 qubits, but one qubit is just a controller for NOT, so for this X Pauli gate, for a second qubit, right? So, if the state of the first qubit will be 1, then this X Pauli gate is triggered. So we apply X Pauli gate, so this quantum negation, to the second qubit. If not, then it's just identity. Okay, so far we've talked mostly about a single qubit or operations on 2 qubits, but the true power of quantum computing comes with quantum parallelism. So if we have n qubits, then on n qubits we can represent all 2 to the power of n numbers that can be represented on n bits. So if we have n bits, then we can represent only one n-bit number at the same time. But if we have n qubits, we can have some information, we can carry some information about all 2 to the power of n bit numbers, right? And our quantum gates may just modify the probability of obtaining one of these 2 to the power of n numbers during the measurement. Okay, so this is another difference and potentially an advantage of quantum computers, right? So using n qubits, we can process all 2 to the power of n bit numbers at the same time. Another difference is that in case of classical computers, results are deterministic and randomness is a pseudo-randomness, in fact. But in case of quantum computers, we may have real randomness, and we can easily sample from probability distributions, which might be difficult for classical computers. And these properties of quantum computers may find interesting applications, for example, in quantum cryptography, or to break some classical cryptography algorithms. So I guess that at least some of you might have heard about the Shor's algorithm and similar quantum algorithms that can be used to just break classical cryptography algorithms in polynomial time, which may also be a bit dangerous. But hopefully quantum computers in the future will be also used for solving combinatorial optimization problems which frequently occur in artificial intelligence, machine learning, finance, transport, logistics. Also sampling from difficult distributions like Boltzmann distribution, which also has applications in machine learning. Simulating quantum processes, right? This can be used for discovering new drugs or new materials. So what we can do nowadays, so it's important to know that contemporary quantum computers are not as powerful as are not powerful enough to just give a real quantum advantage over classical computers in business applications. So at least not the quantum computers that are publicly available and that we know, because it's possible that in some secret laboratories there are already very advanced and powerful quantum computers. But the publicly available quantum computers are still relatively small. So up to this year, the larger quantum computer based on this gate-based model had 72 qubits. This year, IBM announced that soon they will have a quantum computer with 127 qubits. So it's already quite a lot, but beside the number of qubits, there are also some other important factors determining the quality of quantum computers, like fidelity. So what's the noise of a quantum computer? Because we should know that there are also, or there might be also errors when we perform our quantum computers due to the measurements or poor quality of quantum gates. So that's why we also need codes for just improving our quantum gates, so quantum error correction codes. We should also know that there are already software development kits for developing quantum programs. So these are just a few most popular frameworks like Project Q, Qiskit from IBM, Forest from Rigetti, Strawberry Fields and Penny from Xanadu, TensorFlow Quantum, D-Wave Sleep. There are also frameworks for just running quantum programs on simulators of quantum computers. So one of such frameworks is Microsoft Quantum Development Kit. So Microsoft even invented their own quantum programming language, Q#. So the future looks very promising, right? So we can observe that there is a progress. So we should be prepared that potentially in the future there might be a real quantum revolution, right? So we should be prepared on that, and that's why it's important to start advanced quantum education and doing more and more research in the domain of quantum computing. And this is one of the reasons why we established QWorld. So we decided that it might be much easier for us and more efficient to just collaborate globally, so operate locally in our local quantum computing groups, but collaborate globally in order to just prepare good educational materials or just organize some quantum computing events. So these are 5 most important keywords that characterize QWorld. So we are a global organization, so everyone is invited, and people, researchers, enthusiasts from each country. We cooperate. By act together, we can achieve more. This is what we believe. We are very open, so all our educational materials and codes that we develop are open source. We promote diversity, so for example, we want to engage more women and also juniors, so high school students, for example. So that's why we also organize dedicated workshops for such groups. So far, we've organized 70 workshops on quantum computing and programming in 21 different countries. So we've handed out more than 2,000 certificates for people who have successfully completed our workshops. I've already mentioned that we have local groups in different countries. So currently we have 21 the so-called Q cousins. So the idea behind being Q cousin is to create active group on a global scale willing to popularize quantum technologies and to involve more people to the field by working locally and internationally. So our local groups are responsible for organizing workshops in particular countries. So for example, we have Q cousins like Q Poland, Q Spain, Q Czech, Q Hungary, and these local groups are just responsible for organizing QWorld's activities and maybe also some other quantum computing activities in their countries. We also have Q Research Department. So in this Q Research Department, we have several study groups, and there is also a Q Intern program in which the participants work with more experienced researchers on quantum computing projects. So we've already organized two such Q Intern programs, and they were very successful. We also organize webinars, talks, so we invite quantum computing experts from all over the world. We organize contests and hackathons just to promote developing quantum computing code. So if you have any questions, I will be happy to answer. We also invite you to join QWorld. So we have our community Slack. Recently, we've also started moving to Discord from Slack. You are also invited to follow our Twitter and Facebook profiles, visit our website, and if there is no QCousin in your country and you would like to establish a QCousin in your country, we also invite you to join and send us an email, and we'll be happy to have you with us. Thank you for your attention, and if you have any questions, I'll be happy to answer. If you have time, of course.
Hi, Pawel. Thank you very much, and thank you to your organization for joining us and partnering up with us and giving this talk. It was really good. Right now, we don't have any questions, but you've left your contacts, and our attendees will get that info, and I'm sure they will email you with a lot of different interests regarding the Q Cousins program, as you mentioned. I would just like to say right now we're heading into a networking and coffee break, after which we'll be back here at 19 o'clock with Quantum Computing Intersects ML, a talk by Terrell France from the University of Harrisburg. Thank you very much and see you then.
Thank you.